तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome. In this lecture today, let us look at one more case study of commercial DBMS this time. In fact, we are going to look at case studies, the well-known Oracle DBMS and the Microsoft Access DBMS, which is shipped with Microsoft Office suite of products whenever you buy them. In the previous session we talked about MySQL, which is a open source or free software, while the ones that we are talking about or that we are reviewing here are both commercial software that are proprietary and you have to buy it off and which can be bought off the shelf and so on. Now let us have a look at the main structures of these. Firstly, the Oracle DBMS. In this lecture, we are not looking at any specific version of Oracle. Oracle is the DBMS Oracle is manufactured by Oracle Corporation, headed by, of course, Larry Wall, and who has been a pretty early player in the whole field of commercial database management systems. And there have been several versions of Oracle that have been evolved over the years, and the latest version, at least as of today, is Oracle 10G, which is the G here stands for data grids, where the database can sense that it is part of a larger data grid and operate accordingly. That is, a grid is a collection of different databases which could be distributed widely, probably across the world, and while functioning as a single data source or a database. And it's been touted, or it's been kind of targeted towards data warehousing and business intelligence kinds of applications. What are the basic elements of or the building blocks of an Oracle database? When you are talking about Oracle databases, there are some terminologies that we need to be aware of. Many of these terminologies, as we noted earlier, Oracle has been an early player in the field of commercial DBMS systems, and while terminologies have been invented and evolved over time in the academic and research community for database management systems, similar kinds of terminologies and evolutions have happened in the commercial field as well. So sometimes it may so happen that the terminology used that we have used, for example, in this class, might differ from the terminology used in Oracle or let us say DB2 or some other commercial database engine, and so it makes a lot of sense to clear what each of these terminologies mean, or what kinds of terminology mismatches can we have between what we have been using and what Oracle, for example, uses. When we talk about an Oracle server in the database management system, the Oracle server is actually the DBMS server that we know very well. That is, it's the DBMS engine that serves one or more clients. And when you talk about the Oracle database, it is more than just the set of data files that form the database, but Oracle considers its database as a collection of all its stored data, including log files and control files and other such auxiliary files that make up the database. and usually for in the academic community, when we say database, we usually talk about only the data files and the index files. So when we talk about, for example, the storage structure, then when we say an Oracle instance, this refers to a set of processes, that is the set of all processes including Oracle system processes which the Oracle server runs, and user processes created for a specific instance of the database operation. What kinds of languages do Oracle support? Does Oracle support? Oracle, of course, supports the ANSI SQL standard with some extensions of itself that are specific to Oracle, and in addition to the well-known ANSI SQL, Oracle has its own query language called PLSQL. PLSQL is a procedural query language on top of SQL, that is, see, for example, SQL language is in some sense a pure query language, in the sense that it does not have other programmatic constructs like, say, using variables, or well, it has certain you can use certain kinds of variables by aliasing and so on, but generally it does not have the generic structure of any procedural language like C or Perl or some other kinds of language. PLSQL, on the other hand, is a complete procedural language where you can actually define variables, you can define control flow, if then else constructs, and looping constructs, and so on and so forth, and embed SQL statements within these procedural constructs. When we talk about the database structure in Oracle, we usually refer to two different kinds of structures, what are called as the physical structure and the logical structure of the DBMS. The physical structure refers to the storage structure, that is the physical organization of the data on the database, while the logical structure corresponds to what is a conceptual schema of the database that Oracle is maintaining. I mean, logical structure here is the logical structure of the way Oracle manages data, not that of a particular database itself. So the way Oracle manages data itself can be treated as a database by which comprises of several other databases, and which comprises of a larger logical structure and update rules and associations and so on and so forth. Let us look at the physical structure in a little bit more detail. We shall also briefly look at the logical structure as well. When it comes to the physical structure of the database, the way Oracle stores data on disk, it basically stores data in several different files that on disk, and very unlike let us say MySQL, Oracle uses its own buffer management policies for writing data into files. What is meant by buffer management policies for writing data? A DBMS like MySQL uses, for example, if we are taking a Unix based implementation or a Linux based implementation of and we are comparing MySQL and Oracle, MySQL uses what are called as high level system calls for writing data into disk. That means a high level system call essentially says gives a block of data to the operating system kernel and lets the kernel take care of writing the data onto the disk by itself. Now what the kernel actually does is in order to speed up the process, it does not immediately write your data block onto disk. Instead, it keeps it in its own memory, in its own cache that is in main memory, and then flushes it onto disk at some point in time. This cache is called the buffer cache. We saw buffer cache and how buffer caches are come into play or affect DBMS operations when we were talking about database recovery processes, right. So when we write something onto disk, there is and we use a high level system call, there is no guarantee that whatever we have written onto whatever we have written has actually been recorded onto disk. Now if there is suddenly a system failure, then even though our write has returned us returned as a successful operation, and we said we have committed committed some transaction, it may not actually have been reflected onto disk. On the other hand, Oracle uses low level system calls. That means Oracle manages its own buffer cache, and Oracle decides for itself when it has to flush the buffer cache and when it has to write to files and so on. However, it still uses files that are visible from the file system interface of the operating system. So let us look at the files that Oracle uses. So when we are looking at the files here that Oracle uses, we have to keep in mind that the way that files are updated in Oracle is very different from the way that files are updated in say MySQL. So these are some of the files that Oracle uses for maintaining its databases. Firstly, the data files, of course. The data files are the files that contain the actual data, and in addition to the data files, a database is associated with a set of redo log files. Remember what is a redo log file? A redo log file are the set of log files that are used for redo based recovery. We looked at a set of log based recovery mechanisms where you first write data onto the log file, and then after flushing the log file you write data onto the actual database. Now whenever there is a system crash, you just have to redo starting from the last checkpoint in your log file all the operations that have been performed until the system crash happened. So Oracle does something like that. So it maintains a set of redo log files as part of a database itself. Then there are a set of control files which contain different kinds of control information, like the database name or the different file names and the locations of these different files and so on. These control files are also used in the process of recovery. Sometimes they are useful in the process of recovery. And in addition to control files, there are other files like what are called as trace files and alert logs. Trace files are essentially files that track certain background processes that Oracle runs. Oracle basically runs several different background processes that for example the server is a background process, and there are several system monitors that Oracle runs to monitor events and call triggers or enable triggers and so on and so forth. Now trace files essentially track these background files and logs them onto files, and alert logs maintains a log of the major events that have happened from these background process and from anywhere else in the system. The log files and control files, as you can see, are the files that are essential for the process of database recovery. Therefore, Oracle also supports a mechanism by which log files and control files can be multiplexed onto different devices. So when you write a log file, you can configure Oracle so that it actually writes it in parallel to multiple devices. The advantage of this is even if there is in a system crash, even if there is let us say a media failure and the log file itself is lost, we can use these backup copies of the log files from actual devices, from different devices to recover back. So the resilience of the recovery process is increased as part of this. So let us look at the logical database organization now. That is, how is the database organized in Oracle? What are the building blocks that make up a database in a logical sense, and what are the different roles of these building blocks and so on. When we are talking about an Oracle database, in the physical sense, there are only files. Everything is a file, and a file is managed by low-level system call operations. But from a logical sense, each of these files mean certain different things, and they are looked at as objects rather than files. Okay. Now, what are the different kinds of objects that an Oracle database contains? There are what are called as schema objects. A schema object contains definitions of some relevant entity in the database. For example, it might contain definitions of tables, it can contain definitions of views or sequences or stored procedures, indexes, clusters, or links to other databases and so on. So everything is treated as an object here, and the object is essentially in a sense serialized and stored onto disk. So an object for using the object orientation methodology comes with its own set of procedures or methods by which handles or which provides a set of services based on the object's definition. So when we say a schema object represents a table, it also provides methods by which we can access or perform different kinds of table accesses, access a table row wise, access or perform an index search on the table and so on. And in addition to the schema object, there is what is called as a data dictionary, which is essentially the system catalog, and it maintains different kinds of cataloging information for Oracle. So it contains information like usernames and security information, that is access privileges and what kinds of users have what kinds of privileges on which schema object, and information about schema objects themselves, the modification date and the creation date and any other relevant information for any given schema object. Then integrity constraints, which in turn trigger all the stored procedures, or which in turn trigger certain schema objects as which are stored procedures. And then certain kinds of statistics, essentially, for example, that help in performing good query execution plans. We saw the role of cataloging information when we were looking into how do we manage or how do we process a query and optimize a query. Cataloging information contains certain, I mean the statistics here in the cataloging information contains certain estimates on, let us say, how many rows are there in a table, how many number of distinct values are there for a particular column, and which row is accessed how many number of times or whatever. All of this information go into performing or forming a good query execution plan while making the query. And then there are audit trails, that is auditing information about the different aspects of the database. The next aspect of the logical schema or logical organization of the Oracle database is what is termed as the table space. Table space is again an important concept in Oracle, which basically describes the physical storage structures of a given set of tables in a database, and it basically governs how the physical space of a given database is used. We will look into how the table space is organized. They basically contain different segments, and which in turn manages the pages or the disk blocks that make up a particular database. So earlier we mentioned the concept of an Oracle instance. An Oracle instance, like we said, has a specific definition, that is it is in some sense it is a snapshot of the entire Oracle system. That is, it is the set comprising of all processes, that is Oracle processes and user processes, and all of which comprises one instance of a server's operation. Now an instance itself can be logically seen as comprising of several different parts. So an instance is logically divided into what is called as the system global area. What is the system global area? The system global area is essentially the area which in some sense, to give an analogy to operating systems, it is the memory area that is used by a kernel, for example, in contrast to that of areas used by user processes. That is, all the resources and memory locations that are used by the kernel is system wide and globally relevant. So the system global area is in some sense the kernel of the Oracle system. It contains the database buffer cache, which which we saw is maintained by Oracle itself in order to flush buffers onto disk and in order to basically control when buffers are flushed onto disk. Then there is the redo log buffer, which is the buffer cache for the redo log. So whenever a redo log is written, it is actually first written into the redo log buffer, and which in turn is flushed onto disk at periodic intervals. Then there is a shared pool of other resources which we will see. Then in addition to the system global area, when we talk about an Oracle instance, we also talk about the user processes. An Oracle instance again is like I said is something like a snapshot of the entire system. So you might also take an analogy to operating systems, where we say an instance of the operating system is the set of all processes comprising of the kernel process and all user process at any given instance of time. In addition to user process, there is what is called as a program global area, in contrast to the system global area. A program global area is a memory buffer that contains data and control information for server processes, that is where this is a global area. Again there is no specific analogy as such to operating systems here, but you can think of it as a global area which is code specific, that is for the data and control information for the global processes that are happening in the database. In addition, there are certain system processes itself, which are the Oracle processes. So Oracle itself runs several processes in the background, which comprises the server instance or the Oracle instance at any given point in time. So Oracle processes may comprise of the server process itself or the server processes, depending upon whether it is a single threaded server or it's a concurrent server where it can actually serve several different clients concurrently. And then there are other background processes like audit trails and system monitors and so on, which belong to Oracle. So here is a schematic diagram of the system global area. Of course, this of an Oracle instance rather, and of course this diagram is in some sense leaves out a lot of things. That is, for example, the program global area is not explicitly shown here, or and the system processes are not explicitly shown, but generally all of these form the Oracle instance. So the system global area, which comprises of the buffer cache and the redo log buffer, they interact directly with the database files, and user process and of course the server process, they interact with the database actually through the SGR or through the system global area. So there are user processes which in turn which interact with the Oracle server process and Oracle process, which could be server process and possibly other process, okay, and these in turn rather than interacting directly with the database file, to be more correct, this diagram should be the arrow here should come through this thing, that is it interacts with the database or with the disk through the system global area. On the other hand, if you are talking about database files, this logical arrow is correct, which says that logically the server processes deal with the database files. So let us look at Oracle process again in a little bit more detail. Oracle process can be categorized into different forms, namely server processes. Server processes are those which actually handle requests from user process or Oracle clients or other application programs and so on, which send SQL queries to the server process. There are two kinds of ways in which you can configure your Oracle server. You can either configure it as a dedicated server or as a multi-threaded server. and a dedicated server essentially is a server that is dedicated to a particular client, so it can take one handle one client at a time, whereas a multi-threaded server is concurrent in the sense that it can handle many client connections at the same time by spawning different threads or processes if your kernel doesn't support threads and so on. In addition to server processes, there are what are called as background processes, and these there are different functionalities for each of these background processes, and they are created for each instance of Oracle. And one of the main functionalities of these background processes are to perform this asynchronous I/O. That is, they are these processes that mediate between the buffer cache in the system global area and the physical disk. So these processes essentially perform what are called as read ahead or delayed write operations. So when you write onto a disk, your data goes into the buffer cache, and at some point in time a background process wakes up and asynchronously at some point in time a background process wakes up and then flushes all the buffer cache onto disk. Similarly, when you give a read command, your data is read, the relevant data blocks are read from the disk, but at the same time a background process is awakened, which in turn reads several other data blocks also from the disk into the buffer cache, again for performance considerations. So the main functionality or the main requirement of a background process is to provide parallelism for better performance and reliability. So there are different kinds of background processes which take on different roles that perform these asynchronous operations, and usually it is good to distinguish between these kinds of background processes. For example, the database writer process. So this is the process that writes the buffer cache of the data blocks from the buffer cache to the data files onto the disk. Then there is the log writer background process, which mediates between the log or the redo log buffer cache and the log files on the disk. So data processes are managed separately from the log flushing process. And then there is the checkpoint background process. A checkpoint, as we saw in our sessions on recovery based techniques, this basically refers to an event in which all modified buffers are written to the data files. That is, any log data or any data about transactions that have been committed before the checkpoints can now be safely discarded. So we saw what are checkpoints. So these checkpoints, as we saw in the session on database recovery, have to be taken at some points in time, and there is a trade-off between speed or the overhead introduced by the checkpointing process versus how much background data or how much historical data that you need to store in order to perform a recovery in the face of failures, right. So this checkpoint background process is a process that runs once in a while to perform this checkpointing operation. And as we saw in our sessions on database recovery, checkpointing is a costly operation because you need to bring the database onto a quiescent state when you are performing a checkpoint. But there are other techniques by which there are other checkpointing techniques which can obviate this problem, so that you don't have to stop all database operations when taking a checkpoint. Then there are other processes like the system monitor, which performs recovery of an instance. That is, it identifies that when the system comes up, it identifies that the system had crashed and performs redo based log recovery. Then it manages storage areas, and it also manages any kinds of recovers transactions that were skipped during the recovery process. Then there is the process monitor background process. It performs recovery operations whenever a user process fails. Note that failure of a user process can also leave the database in an inconsistent state, especially when it is in the midst of a transaction, and especially even more when transaction data are written directly onto disk. So if the user process fails to complete the transaction, then the database is still in an inconsistent state, and then you need to recover. But then this is different from a system monitor in the sense that the entire system has not crashed, so other transactions are running, this recovery process has to be handled separately. There is also a process called the archiver process, which archives the online log files onto archival storage, essentially for backup purposes. We also saw some mechanisms of archival when we were talking about database recovery techniques. Then there are recoverer processes which essentially are useful when Oracle is used in a distributed database setting. We have not as yet looked into issues pertaining to distributed databases, but there are several issues when database is distributed across several different clusters, especially to detect that a particular transaction that is spanning across different machines has actually crashed, or it is pending, or something of that sort. Then there are other processes like dispatchers and log processors, where dispatchers in multi-threaded configurations, they route requests from user process to the appropriate or the available server process. And then there are locking process which are in some sense again monitors that monitors locks between across different instances when Oracle runs in parallel server mode. Now let us look at SQL in Oracle. What kinds of SQL statements are handled? As we noted earlier, Oracle supports ANSI SQL. In addition to ANSI SQL, it has its own extension to SQL, namely the PL SQL, which helps the user to embed SQL statements into a procedural language. But as far as the support for SQL itself is concerned, Oracle supports all kinds of standards, data definition statements and data manipulation statements, and it supports transactional semantics, full ACID semantics, then other kinds of constructs like session control semantics, and even embedded SQL statements. In addition to support for SQL, Oracle comes with an elaborate mechanism for methods and triggers, and these utilities were added to Oracle as part of its object relational extension. So Oracle essentially is an object relational database, where we have not again as yet seen into what constitutes an object relational database, but essentially a database that uses object oriented semantics like method calls and triggers, and triggers are also some kinds of method calls, and inheritances, associations, and so on. So a method is actually a function that is part of the definition of a user defined data type, and it's slightly different from a stored procedure in the sense that a program, essentially that is a user program, invokes a method by referring to an object of its associated type, but stored procedures are actually called from SQL statements independent of any particular object as such. It is only the database whose context is necessary for stored procedures, and Oracle methods have access to attributes of their associated objects and information about their types. So a method, for example, an Oracle method for example would be a method in one of the schema object. Let us say a schema object represents a table, A method would be some code which says how do we access the next row in a table, or how do we get the primary key field of a table, and so on. So get primary key, or get next row, or a query or something of that sort, which abstracts away the implementation or the storage structure of the table from the database engine as well. So this is different, slightly different from the stored procedure concept, because stored procedures are visible to user programs or SQL constructs, while methods are essentially, I mean, the methods are visible to user programs only in an object relational context and not in a pure relational context. And triggers are those methods which have active rule capability, that is, which are called automatically in response to events and conditions. Let us have some more deeper look into the storage organization of the Oracle database. We noted earlier that storage is managed by what is called as a table space. Now, table space is the space that manages the physical organization or physical allocation of memory or disk blocks for a given database. So, database is divided into several different table spaces, and among this we can distinguish between what are called as the system table space and the user table spaces. A system table space is maintained for maintains essentially all data that are visible only to the Oracle system, while the user table space maintains data that are accessible by user programs, and data files are stored or are managed by the table space itself. Now, every Oracle database contains a unique system table space, and this is labeled as system in caps here, and the data dictionary objects and other system wide information are stored in this system table space or are managed by the system table space. Now, the physical storage itself, I mean, how does the table space manage the physical storage? The physical storage itself is divided into three different kinds of storage, what are called as data blocks and extents and segments. A data block corresponds to what is called as a page in or data page in several other database systems. It is the smallest level of granularity in which data is stored. Data blocks data blocks usually have a one-to-one correspondence with the disk blocks or the granularity with which your disk accepts data. Most of the at least all of the disks accept data in terms of one sector size of the disk, but there are some disks with enhanced capability that can actually read and write multiple contiguous sectors at the same time. Now, this multiple contiguous sectors form one data block, and an extent. The term extent is used to refer to a specific number of contiguous data blocks. So, where data block is the minimum unit of storage. Now, a set of segments that are allocated to a specific data structure like a table or an index or something like that is called as a segment. So, data blocks again each of these let us look at each of these different elements in a little bit more detail. Data block, whenever a particular data block is stored, it contains the following information. It contains some header and table directory information which talks about which table it belongs to and pointers to other tables and so on, and there is a row directory information which talks about which are the specific rows that are stored in this data block, and the data that pertains to a row, and any free space information if there is any free space left out in the in this data blocks. And an extent, as we said earlier, is a set of contiguous data blocks. So, whenever you create a table, Oracle allocates an extent to it, and an extent is extended in a sense, that is an extent is more extents are added to the table as and when extents become full. and these extents are managed by segments. That is, we saw that a segment is a set of different extents, and extents allocated in extents can be allocated for any given data structure like tables or indexes and so on. So if I allocate an index an extent to an index, the extent remains allocated as long as the index exists, and is automatically freed when the index is deleted. And a collection of extent is what is called as a segment. So there are different kinds of segments, what might be termed as data segments and index segments. And data segments are those which store data or which handle elements that are stored in the data files. And a data segment belongs to each what is called as a non-clustered table, and to each cluster. What is a non-clustered table? As we noted earlier, a cluster is a collection of machines on a LAN which gives us a single system interface. Now a clustered table is something that is spread across the cluster, that is, a part of my table is in one machine and part of it is in another machine, and so on and so forth. Now for every such part in a given machine, a given data segment is allocated, and index segments are allocated for every index structures that's been created on these tables. So every create index command will allocate an index segment. There are also other segments called as temporary segments, which are used as temporary work areas, especially to store intermediate results or to allocate data for virtual tables or results of an intermediate query and so on. And then there are rollback segments that are used for undoing transactions. So like MySQL or any other DBMS, Oracle servers are usually expose several different APIs, so that user processes or application programs can directly talk to the Oracle DBMS. So the SQL support or embedded SQL support is provided for different languages like COBOL, C, Pascal and so on. And in addition, Oracle has its own procedural language like called the PLSQL. Let us have a brief look at how PLSQL looks like and what kinds of operations does it provide over and above plain vanilla SQL. Okay. PLSQL as we noted earlier provides procedural constructs within which SQL constructs can be embedded. A PLSQL block can be divided into three different parts, what are called as the declaration part, executable part and the exception part. As you know, if you notice correctly, this is very similar to how a typical procedural language is also ordered, except for this exception part, and out of these three parts it is only the executable part that is mandatory. So the declaration part is where you declare variables or and any other characteristics that are functions that PLSQL uses, and the set of statements or the set of executions is embedded within a begin and an end construct here, where you have the set of statements as well as the exception handlers, that is the executable part as well as the exception part written within this block, that is within this begin and end construct. So the declaration part, like we noted, is used to declare variables, and these could be variables that are used in both SQL and PLSQL data types. And the SQL and the executable part contains both SQL commands and PLSQL constructs like if then else or for loop and while loop and so on. So you can say if some condition, then send this SQL statement, else send this other SQL statement and so on. And the exception part handles error conditions whenever an exception is raised, and errors could be either system errors that are flagged by the database itself, or they could be user defined errors that are flagged by violation of for example some integrity constraint. So let us summarize what we have seen in Oracle before having a brief look at MS Access as well. Oracle is a very popular commercial database management systems. So it's a commercial one, and it's in contrast to MySQL, which is an open source DBMS, and the latest version 10G supports data grids as part of Oracle, and Oracle actually supports not just relational, it also supports object relational databases, spatial databases, and databases of sequences, and so on. So the different kinds of data can be stored in Oracle rather than the pure relational database. And it supports procedural constructs over SQL in the form of PLSQL, where you can write control flow constructs, if then else, and while loop, and for loop, and so on. And Oracle supports transactions and log based recovery. It also supports clustering, where you can have a data file that is clustered over or a table that is distributed over several machines in a cluster, and several other features. Let us now briefly look into the second commercial database whose case study that we are seeing, which is the Microsoft Access. Microsoft Access, we have included Microsoft Access as part of this case study mainly because it's a commercial database which is kind of tailor-made for ease of use for a non-technical user, and where everything can be performed using graphical interfaces. So the setup time and the learning curve for this database is much smaller than any other commercial database like Oracle or other database like DB2 or and even probably MySQL. So Microsoft Access provides a database engine and a GUI based, that's a graphical user interface based mechanism for almost anything, that is for data definition, data manipulation, queries, and reporting, and almost anything to do with a database can be performed using graphical user interfaces. And but it's not that it's only through the GUI that MS Access can be accessed. You can also access the database using basic, that is Visual Basic, and several other macros that you can write to form your own procedures and so on. And one feature of MS Access is it provides hyperlinks, that is URL as a native data type, which is generally not supported by other databases, where you can treat a URL as a data type by itself and not as a string. So what are the different components of the Microsoft Access database? It's called the engine of the Microsoft Access database. All data that for a given application are stored in a single file called which has a suffix called .mdb, and but even then you can access these MDB files through different ways using the open database connectivity mechanisms. We have not talked about ODBC as yet, but generally ODBC essentially is a common interface by which you can access several different databases as though they were data sources using a single common interface. And MS Access provides support for data validation and concurrency control using logs, but not full ACID semantics, and it also provides some amount of query optimization. What kinds of GUIs are available? We have some screenshots which you will also see of these GUIs later on. There are GUIs that are available for specifying the structure of a table, formatting of the field layout, any kind of masks which talks about invalid inputs, and validation rules, default values, data types, index structures, and anything to do with database design can be specified using graphical user interfaces. You can also use GUIs for defining foreign key relationships, and you can also enable what is called as an automatic inference of relationships. That is, whenever you use the primary key field of one table as an attribute of another table, there's automatically MS Access would infer that there is a foreign key relationship. It also provides this facility of an automatic inference of relationships between different fields. Then queries can be graphically posed through what is called as a query by example interface. That is, you can formulate, or you can graphically show how your query should look like. That is, I should have these tables and these tables and these tables with these associations and so on as part of my query result, and then say, now give me the query. Okay. So there is a QBE interface or a query by example interface, and as and when you build your query as part of the QBE interface, programmatically there is an SQL statement that is being created to which also you can switch to and change your query whenever you can. And you can perform joins by drag and drop operations between tables, and you can form addition and deletion of attributes to tables using drag and drop. Then there are what are called as expression builders, where in which you can specify the constructs of the where clause of your SQL query. Reports generation again can be performed in a GUI fashion. That is, it's an integral part of the Access database. The Access database doesn't just return a query and leave it at that. You can actually specify how the returned data should look like in the form of a report. Let us say in a page where different elements of your query go into different parts of the page. So it becomes a reporting mechanism, and the reporting whatever reporting mechanisms that you have created are tightly bound to the underlying database tables and queries. So there are different report generation wizards which help you in showing how a database report can be created, and different styles in which a report can be created. So many other additional features, what are called as cross tab queries, which wherein you can perform group by on a specific values within a column and aggregating within the group that you have performed the group by on. And the tables that you have generated or your database are available as OLE objects. OLE is the well-known object linking and embedding mechanism that are used across different Microsoft applications. Therefore, you can, for example, you can actually use your database table as an embedded table in a Word document, for example, or in a PowerPoint presentation and so on. And there is a user level security based on login and password that is based around the NT server model, and it also performs multi-user, it also supports multi-user operations and concurrent clients and so on. So to summarize what we learnt on MS Access, MS Access is a DBMS system that is meant primarily for the non-technical end user, where the learning curve is much smaller than in using, say, Oracle or MySQL or any other larger commercial database system. It is shipped with the MS Office suite. So whenever you buy the MS Office suite of packages, MS Access usually comes shipped with it. And the main feature of MS Access is the GUI, or the graphical user interface, which can help you perform almost any database operation, whether it is specifying your database or formulating queries or reporting or any other kind of database operations. So it gives support for graphical query specification and also report generation, and these databases are available as DSNs or data source names through an ODBC interface, that is any database client that is compatible with ODBC can access MS Access databases as easily as it can access other ODBC compliant databases. Oracle also is ODBC compliant, and several most widely available databases are ODBC compliant. And these tables are database objects in MS Access are available as OLE objects that can be linked or embedded within other MS Office or within other Microsoft applications like say MS Word or Excel or PowerPoint or so on. So let us have a look at some of these screenshots here that show how typical MS Access or working with MS Access looks like. So when you start a database, this is what you get, that is you can start a database where you can specify your database design using different views. There are what is called as the design view, or you can create tables using a wizard where it can where it will automatically fill up certain well-known fields in a table, or suggest you for certain structures for your database, and or you can even create tables by actually entering data using a form. This screenshot here shows an actual form in which by which data can be populated. So here there are two different forms for two different tables. There's a table called mailing list, and there's a table called assets, and these are the different fields that that go into this list. So you basically fill up this form, and the data is actually stored onto the database. The last screenshot here shows how you can graphically build a query using the QBE interface or the query by interface. The window here essentially says that or the user who is formulating the query has said that the results of his query should contain these 4 different tables. Okay, out of these 4 different tables, these are the fields that are required, and the user can specify and basically there's a show which can be clicked or unclicked, which will say what to show in the table, and the criteria can be specified here, which will say how to formulate the query. So that is the beauty of this MS Access databases. So with that we come to the end of this second case study.